Hello and welcome to week 5 TA session. This is week 5 TA session for biointerface engineering. So in the last week, that is week 4, in the last weeks of week 4 and week 5, these were the topics covered. In week 4, protein adsorption, characterization of protein adsorption and kinetics of protein adsorption was taught. And in week 5 covered the topics on aggregation of proteins, kinetics of protein aggregation, and effect of surfaces on the aggregation of protein. So this week also we'll solve the week 4 assignment and some sample questions for week 5. So this was the first question. The building block of proteins are, the correct answer is amino acids. So proteins are polymers with each mer made up of amino acids. The second question was the peptide bond is the linkage between. Here the second option, that is amine and a carboxyl group, will be the correct answer. So the end carboxyl group of one amino acid and the amine group of the starting amino group of the next amino acid, they form the peptide bond. Forces stabilizing the protein structures. So here all of these would be the correct answers. Hydrogen bonds, electrostatic forces, and disulfide bonds. All of these structures help in stabilizing the protein. How many amino acids are present in one turn of the helix of protein? So there are 3.6 amino acids present in one turn of the helix. As you can see here, in one turn, pH is 5.4 angstrom and there are 3.6 residues of amino acids. This was the next question. For the transition of a protein from native to unfolded structure, if the standard Gibbs free energy delta N to D G is minus 17 kilojoule, then the correct answer here would be the unfolded state is more stable. So the Gibbs free energy from native to unfolded structure is given as delta enthalpy to native to unfolded minus T delta S. So the negative value of this implies that the N state is more stable than the D state. Therefore, the unfolded state is more stable in this case because it is negative. The protein stability depends on, so all of these parameters, pH, temperature, and ionic concentration, all of the protein stability depends on all of these, and changes from the optimal pH, temperature, or ionic concentration affects the stability of the protein. Now the next question was functional activity of a protein depends on concentration, volume, native configuration, none of this. Here the correct answer would be the native configuration. So the native configuration, the protein is folded in such a way that it can bind to its active site and start its function. So the native configuration is essential for the functional activity of the protein. Here is the next question. In the quartz crystal microbalance, the frequency of crystal vibration decreases with increasing absorbed mass. The third option would be the correct answer. As you can see in the plot as well, where delta F over time is given, and with increasing mass over a time, the frequency is decreasing. This was the next question. What region of infrared wave is considered in Fourier transform infrared spectroscopy? So here mid IR region would be the correct answer. So mid IR region ranges from 2.5 to 25 micrometer or 4000 to 400 centimeter inverse. And within this range, all the alpha helix, beta sheet, random coils, and beta turns can be detected. So the mid IR region is considered for FTIR spectroscopy. Now this was the next question. Protein adsorption is typically higher on. The correct answer here would be hydrophobic surface. The protein is more able to interact with the hydrophobic surface and gets adsorbed than on the hydrophilic surface. Now we have some week 5 example questions. This was the first question. What does thioflavin T detect? So here the correct answer would be beta sheet. So the thioflavin T detects beta sheets, and that is how it helps in measuring unfolded concentration of unfolded proteins, uh, concentration of unfolded proteins, because the unfolded proteins have more beta, denatured proteins have more beta sheet, not the unfolded, the denatured ones. Which of the following is not a common supersecondary structure in proteins? So beta sheet, the options are beta sheet, beta alpha, beta unit, alpha helix hairpin, and beta hairpin. So here beta sheet is not a common supersecondary structure. Beta sheet is just a secondary structure. Rest of the options, that is beta alpha beta, alpha helix, and beta hairpin, these are all supersecondary structures in proteins. All but one of the following disease is associated with protein aggregation. Which of this is not? So here Alzheimer's, amyotrophic lateral sclerosis, and Huntington's disease, all of these are associated with aggregation of protein, whereas COVID-19 is not. And this is our last question. Raising the temperature from room temperature to 100 degrees Celsius. So this will break ordinary covalent bonds but not hydrogen bonds. Will break both hydrogen bonds and covalent bonds. Will break neither hydrogen bonds nor covalent bonds. Or will break hydrogen bonds but not covalent bonds. The correct answer here would be it will break only hydrogen bonds but not covalent bonds. At 100 degrees Celsius, that is the boiling point of water, you can say the hydrogen bonds within them is broken but not the covalent bonds. Okay, so this was all for this TA session, and we'll see you next week. Thank you for joining.